Do you want to introduce you briefly, because you're the only one we didn't introduce this morning?
So, hi everyone, I'm Eva Portelance, and I'm an assistant professor in the Decision Sciences Department at HSC, and also at Mila, and I work at the intersection of cognitive science and AI, looking at questions of learnability, how we learn language and how we learn reasoning skills, both in humans and in machines.
All right, wonderful. Okay, so let's get started. First of all, you don't have microphones. This is not good. Karim, can we solve this? Because they cannot shout. Thanks so much. God. All right. I think my first questions for you to get things started were, are artificial neural networks really reasoning or just parroting? And sort of the motivation for that question was that yesterday we had a very controversial take from Paul Cishek, trying to make the point that mostly large language models in particular were parroting rather than understanding anything. So this is a reasoning thing. I feel like, Taylor, you answered that question really thoroughly in your talk, but maybe let's hear the different perspective on this. So reasoning or parroting, just in a sense, reproducing the training set, or actually extracting deeper reusable meaning?
I'd like to hear more from Taylor, because I like your way of thinking about both similarities in behavior and similarities in mechanisms. Yeah.
So, does this work? Hi. So the question is, are language models really reasoning, or are they just parroting the training data? My answer is yes. I think they're doing both of those things, and I also think people are doing both of those things. Of course, at different times, people parrot things, people rely on the simple heuristics and biases sometimes and aren't really truly reasoning. So there's some distribution of really reasoning and parroting the training data that I think both people and language models do. And then there's a further question about different types of reasoning that I was getting into in the talk. And I think there are definitely certain types of reasoning where, for instance, mathematical reasoning, physical reasoning, where language models are still, basically, if it looks like reasoning, it's parroting, and they're not really getting the problem, right? But so I think it's a complicated question both for people and for the models.
All right, so Luiz?
Is this on? Yes? Yeah, so one thing that I find interesting as a non-AI person, so excuse me for that, and a neuroscientist, is that, for instance, I really enjoyed your talk, but one of the things that strikes me is that sometimes there's an emphasis on certain capabilities, let's say reasoning, and the way you approached it was with problems that some humans have difficulties with, right? Like, the Raven's matrices, or analogical problems with spatial configurations and so on and so forth, which kind of reminds me, because given that I'm so old, it reminds me of early times in AI where we thought what really mattered was some capabilities that we thought were the apex of, I don't know, like cognition or intelligence, like playing chess, playing certain things, or doing some kinds of purely cognitive operations that happened to be a little bit more amenable to progress, even in the early versions of AI, which are not even a shadow of what we can do today, but were amenable to some progress, while problems that we thought were really easy, like sensory motor coordination and some other kinds of very basic decision making that were situated in environments and had to do with the value of one's goals and actions and plans, really proved to be insurmountable. And so it feels to me that I think the question is fascinating and important, and it needs research, and the kind of research that you were doing is definitely part of what needs to be done. But it feels to me that we need to kind of remember that whatever we call reasoning or intelligent capabilities needs to be a little bit broadened, because otherwise we'll forget some of the same issues that we faced for many decades. I mean, it's my impression at least.
Yeah, I just want to echo what Luiz said, because I think that's a very good point. indeed, a lot of what people talk about when they say reasoning in LLMs is math and coding capability specifically, right? And a particular kind of math, which is sort of grade school math. And, coding maybe because we want to replace ourselves, I'm not really sure. But, that's a very narrow kind of range of reasoning capability. And so it's interesting actually to see some of these analog tasks being looked at as well. But one of the interesting aspects is that in some ways, LLMs are for sure capable of reasoning. So there's actually one very recent paper from my colleague Dale Shermans and his colleagues, which is a very heavy math paper, but basically showing that you can take an LLM and make it implement a sort of a canonical Turing machine, okay? So make it implement exactly a formal system. Now, if you think about what the implication of that is, formal systems are systems that perfectly extrapolate, right? They can take any input and they'll compute the right function on that input. And so the fact that you can prompt an LLM to do this means that in a way you can get it to reason very much exactly about some specific kind of function, right? Is that going to make it better at reasoning tasks in general? Probably not. Definitely not in the context of embodied intelligence or sort of situated intelligence. That's kind of a bar that we are very far from right now.
Actually, to frame this dialogue, suggestion from Karim was, so long time ago there was this idea of the Turing test, at which point wouldn't you be able to tell if you're interacting with a machine or a human? And, I guess ChatGPT smashes that, so check. But what would be an actual good Turing test for reasoning? Like you're saying, okay, we can get it to program anything, okay, including nonsense, I guess. But do you have ideas along those lines?
Yeah, well, I want to make a point. So coming from a linguistic background, I'll use an analogy from linguistics in terms of LLMs, we refer to them as sort of black boxes, and the way that we often evaluate them is simply based on like observational adequacy, as we'd say, like their external behavior, and we rarely have the opportunity to sort of like look inside at what explains that behavior. And so I think it's very difficult for us to evaluate things like reasoning where, say, let's take the example of numerical reasoning. We have an intuition in terms of how humans do numerical reasoning, and we have an understanding of how that may work, but there is a possibility that these models are learning a very different numerical system that works in the context that they have been exposed to. They may not necessarily be exactly ours, but still reproduces. And so in most contexts, in the context where we're looking at like observation-based evaluations. And so it's very difficult, I think, for us to design tasks that'll tell us what that process is. Currently, the best we have is, do they reproduce? Which kind of goes back to your first question, which is it's very hard for us to tell that difference, right? Is it parroting or is it really something like an actual system? And what does that system look like?
I would just like to emphasize something you said. Like one of the points I believe Paul made, and I mean, if he's here, can correct me if I'm, not representing his ideas correctly, but was that in order to have true understanding, you need to extract representations that were useful. And what implied by that was very much, what Doina told us about, useful for planning, evaluating affordances, and so on. And he contrasted that with large language models, which are, trying to fill in the blanks. However, filling in the blanks in a complex text is very much like, actually taking actions in a complex environment, being given a context. So do you believe there is a qualitative difference between self-supervised learning in language model and actually taking action in a world reinforcement learning? Or are they, in a way, messing with the world, just a world only composed of letters or tokens?
And I think right now in a way, code is the answer, and that's partly why people are focusing on that, because the way that these models can definitely touch the world is by writing code and then having that code execute and do something, which can include, moving a robot arm or, fetching information or, looking at photos and trying to generate something new. So there's definitely action that's
actually
available.
Useful?
useful devices.
Well, I mean, if they pilot robot, I guess they can.
I mean,
you know.
I think at the moment so useful is an interesting question. At the moment, I think we are finding these very interesting. There's a lot of interesting use cases, a lot of unexpected stuff. I don't think we yet understand how to use these models in a real way. A lot of people, almost everybody that I know has interacted with these systems and used them for something, but a lot of it is entertainment, and some of it is answering simple programming questions that are going to be on a test, and not clear if that's useful or not. I think we're still a couple years at least away from understanding what's a real application where these things will make an impact.
Wonderful. Just to say, Oiwi, please you're welcome to jump in at any time. I know this topic is a little bit further from at least what you presented, but, I'd like to hear from you as well.
Yeah. Yeah.
I mean, I don't want to throw you under the bus. Welcome to joining the conversation, but...
I think I was just sitting here thinking about observational adequacy from linguistics, which is contrasted with descriptive and explanatory adequacy, and thinking about what Taylor was saying about matching the data and the mechanisms, and wondering how good of an analogy is it? Like, obviously, we have these models which are explicit, so we like to look at them and think about how they can map back to things about humans. And so that's kind of, it's exciting, and we have those questions raised. But is that, like, how bad is that really? Like, are there limits? How are these systems different? And like, what are the limits of that kind of approach?
I think, I'll just say, I mean, currently, I think we don't know. I do want to maybe actually push back a little bit on the idea that we can't infer anything about the internal mechanisms just from the behavior. I do sort of, as a cognitive scientist, I believe that we can infer things about the mind through clever experiments, right? But ultimately, of course, as a cognitive neuroscientist, also, like, it's useful to also look directly at the brain. I think it's going to be extremely useful to look at the internal mechanisms in these systems. And one, amazing opportunity that we don't have with the brain is, like, these are systems that are in some cases capable of, doing some higher order cognitive functions, and we have perfect access to their internal states. So we can study them in a way that we, couldn't study the human brain even if we allowed ourselves, like, invasive experiments, right? So I do think they're very useful as a tool for understanding reasoning. I personally don't find them super useful, like, in my everyday life, but I think they're fascinating as a scientific phenomenon.
Can I follow up?
Yeah.
So I was sitting there listening to your talk and thinking, because you're talking about these models are kind of like people if you put them on the spot and you don't give them time to think. And I was like, I wonder if you've looked at, like, inference time compute, like if you add more compute. And I was like, I wonder if they'll become more like human. But then I was like, is that the right way to think about it? And what would it mean if it was more similar? It's not like, are humans doing inference time compute? Like, it might behave similarly. We might have similar. I like how you're looking at generalization and, like, are the patterns of errors similar? And you can infer maybe things about the representations, and you can look at the models. But yeah, I was wondering, is this like some kind of category error that I'm making in my head, just because, like, we're thinking about AI and we're thinking about the brain, and I'm kind of looking at the intersection in my head?
So I'd like to actually follow up on that, because that connects to another topic I wanted to bring up. So the general question was framed like, what do you think about the scale of development for reasoning? And by scale, I mean, I was thinking more data size, but it's interesting also to think about it in terms of actual, time spent, if we're talking about a robot or an agent exploring an environment. And maybe just, like, restate something, Doina, you were hinting at, as this idea that maybe adding bottlenecks, adding the time of evaluation as a metric may actually push for interesting affordances that we may not get into those models that are, like, godlike but very, very slow.
I mean, if you there's definitely impacts of inference time compute, right? Like, for people who played around with O1, which is the sort of the newest OpenAI model, right? It's more geared towards this kind of math coding type of reasoning tasks, And it's got these really long traces of essentially some, distilled description of reasoning steps, and it takes a lot more time. And the reason it takes a lot more time is that it's running this sort of essentially a search, right? A more extensive search over different paths of solution at runtime. I think what we don't quite have right now is a system that continues scaling with that time, right? So, that sort of fully continues scaling in the same way that we scale with data. I think with data, scaling laws are kind of, they're still holding. But inference time helps up to some extent, and then at some point it doesn't, and it also depends on the size of the model and all kinds of other things. So I don't think we understand exactly how to use it efficiently right now.
Other people? Oh, Luiz?
Yeah, so one thing that I wanted to discuss, it was in Doina's talk that I thought was extremely relevant, it was that constraining the situation and the goals of the agent seems to me to be a key to be able to at least reason like biological organisms. So if we think about search spaces, unconstrained search spaces essentially make no sense biologically because of survival, right? And so there has to be some form, mechanism, process, whatever, that guides you into some narrow portion of the space of relevant, effectively, motivationally, cognitively relevant types of actions or decisions or following up on this situation that you're in. So I think that we perhaps could learn a lot from biology, from neuroscience, and from animal behavior in trying to understand how these processes are time constrained by definition and always revert back to some kind of situatedness. You can't have an agent that is just floating on the ether, and it has to be situated in some sense in which its context determines how it will progress in its actions, right? So I think that somehow that seems to be a little bit lost. It appears to me from what I hear from the researchers, and what I thought it was very inspiring in your talk is like, let's limit this, and it might feel like a problem, but it might be a path to something quite different, right? Because the bottlenecks, we have huge bottlenecks of processing, right? So I can't process everything that is going on here. I can't consider all the alternatives, and so it's very directed. So how does that directedness help in some general processes?
Yeah, well, I think that gets to like inductive biases, be that in the learning functions, in the architectures, or in the choice of data we decide, or the distribution we decide to consider in the context of language models. And I think there's a growing community of academics who are particularly interested in downsizing models and sort of countering this trend towards scale. And the solutions that are being explored there are solutions where we are trying to sort of induce these biases in some way or introduce them from the start in one of these three categories, right?
So, thanks a lot. I didn't mean to interrupt. I just want to make sure people, if you have questions, don't hesitate to come here. We're going to move on to question from the audience in just a few minutes.
So I'll just briefly add, I think, I've been studying the topic of inductive biases in neural networks for a few years now, and I think it's important to keep in mind there's sort of two different goals you can imagine one having when you're studying the human brain, which is extremely data limited, extremely time limited, or brains in general, versus if you're an engineer trying to build a system. And I think it's conceivable that the sorts of inductive biases that are necessary to induce reasoning in systems that have virtually infinite amounts of training data are not necessarily the same inductive biases. Like both things could be true. Inductive biases could be central to explaining brain function and maybe not totally necessary in any particular engineering setting.
I've been biting my own foot, but there is this evolution bit that is left out for a lot of reinforcement learning research just because it's too computationally expensive. It's so inefficient that it moves much more slowly than other approaches. But at the end of the day, that's how we evolved ours. We're not optimizing for a function. We're just there because we're good. The proof is in the pudding. Okay, Marie.
Hello again. I was just going to comment that I think one of the concepts you introduced, Doina, during your talk about the graceful decay is, I guess you can think of it as a limitation of the system of how much you can learn, but also I think it's quite a key, at least in human learning, is a key mechanism to drawing meaning and lessons from an infinite amount of exemplars. And I think that putting in that kind of bottleneck is key to building systems that aren't just stocking infinite exemplars that don't connect to and don't apply to the world. And so, yeah.
Yeah, thank you for the comment. I mean, I also think that that's quite key. And it's, again, something that in RL is a very foreign concept in the sense that people think a lot about optimality and also think about performance being sort of uniformly good along a distribution that you could see in the long-term future, right, in the infinite future, because we often talk about the stationary distribution. And yes, it's weighted by, where you're actually dwelling in more, but it is sort of not necessarily thinking about this kind of, minimal difference or, how does performance degrade as you see more similar examples, but not identical. And I think for people, especially that are interacting with some of these agents, it's jarring if the agent is making a mistake that you think it shouldn't, right? And some of it we're patching now. So for example, with LLM's interaction, we put things in context. If you put enough stuff in the context, you kind of get it to, what comes next is going to be similar enough to the context, but we're sort of dragging by force these agents into being in a situation that's very similar. And yeah, we need some mathematical tools to sort of formalize this idea of graceful degradation.
Right, thanks.
Hi. So just, I think it's a follow-up of the point that Luiz rose before, which is like we used to think about like those apex of tasks of like chess and Go and and so thinking about the capabilities of things in terms of tasks is strange to me. Like how magical multiplication is very easy for computers, but not for us. So can our idea of intelligence be decomposed into different types of reasonings? And the idea is if a machine checks enough of them, it'll be AGI, or a different way of thinking about it is, are tasks a good way to think about intelligence, or are they an illusion of our capability of abstraction, actually?
That's more like a comment, really inspirational. Follow up.
Maybe I can bring the point of development in here, where humans, obviously, we're not born directly with the brains we have as adults. And so I think the fact that we learn different reasoning skills at different points does suggest that they are, to a certain extent, differentiable, though they may have, on occasion, relations where they are related, like you need one to learn another. And so, at least from like the human perspective, I would say that yes, we are probably learning some. Reasoning should be seen as a multitude of different types of skills that may be related in some sort of hierarchical way. Whether that's the case in models, I don't know. Probably not. But maybe that's an interesting direction to explore in terms of novel model design when we start to think about can we do something that's a little bit more neurosymbolic in terms of our architectures to try to sort of emulate that process. Maybe that gives us reasoning abilities that are more biologically plausible in terms of how they react in certain contexts versus others. I don't know, yeah.
Just add something. So yeah, I like this question of like, are there really these distinct sort of islands of reasoning capacities, or is it this more interactive thing? I think it's absolutely a more interactive thing, and maybe it's not even reasonable in the end to try to like form like a perfect taxonomy. I think there are, different factors or components that contribute to reasoning, and most tasks involve, especially real-world tasks, involve some complicated interaction of these things. And that makes it really difficult to evaluate these systems. You give it a task, it can't solve the task. There could be any number of reasons why it can't solve the task. And so this is kind of the spirit of some of the evaluations that I was presenting in my talk, where you try to strip away things, different factors that might be contributing. But ultimately, I totally agree that it's going to be a much more interactive thing. Anything that we would actually call reasoning in a human sense is going to be a complicated interaction of a lot of factors.
Hi, thank you for your talk. I just wanted to expand this question that was asked before on LLMs being used in kind of an RL context. And for context, I was at a summer school in Prague over the summer. I ran into these mechanistic interpretability researchers who were trying to do various aspects of planning and reasoning for these kind of almost RL frameworks like chess. And it was very interesting to see that they would find existence of phenomena that you see in RL, like the primacy bias. And what we were trying to do is kind of describe these kind of classic RL definitions for these kind of large language agents, like an action space. So I guess I'm curious on your perspectives on these kind of definitions on what would the action space of a dialogue agent be, and whether these definitions are generalizable or have limitations.
Yeah, that's a really interesting question. So I think there is definitely a lot of potential use of LLMs for RL of different types, right? So one use that has been explored is using the LLM to provide the reward signal, right? So I've had a student that worked on this, code as reward. There's the motif paper. There's various papers that are essentially using an LLM to generate code that will provide the reward for an agent based on images and other stuff. Similarly, you might think of the LLM as providing affordances, right? Or you might think of it as providing a space of actions, right? Or a space of options that are now not policies in the sense of there's a network, you put in an input and an action comes out, but there's actually a procedure, right? And there's code that runs, and that code can be a lot more interesting, right? So the space really opens up in terms of the kind of temporal abstraction that you might get out of an LLM by leveraging its sort of inherent knowledge of coding. Right now, all of these things are quite brittle, right? Because the code generation is a bit fuzzy around the edges, and that these things require a lot of babysitting. But as code generation gets better, we can definitely leverage that knowledge. There is this issue of using the LLM as a world model, and there's some people that really are trying to get to that point. I think this is a lot trickier, basically because, at least in my opinion, situated agents are currently sort of one step removed from the LLM. So understanding what's situated, what's my current state, unless I can describe it in tokens to an LLM or in an image, it's kind of hard to make that explicit. And so there needs to be this sort of step in between whatever the LLM is trying to use to predict and whatever my state is. It's not really clear how to bridge that without actually going to agents that are embedded in an environment, and they're, maybe the LLM is part of their architecture, but they also have something that is really directly grounded in interaction. By the way, I think the work on mechanistic interpretability is really fascinating, and trying to understand exactly what's going on inside and what kinds of things can or cannot be represented. It's a really cool direction, not just for interpretability, but just to give us a bit more understanding of the current systems.
Could I ask a follow-up question? I like this topic. Some people say, LLMs aren't embodied, right? So this is one limitation. So you might imagine that there are gaps in its ability to understand things like affordances. Do you have thoughts about, could we, slap, robotics onto LLMs and make them smarter? Or?
I think there's quite a few people that are very excited about that prospect, especially in there's been a flourishing of startups that are trying to do this kind of thing. One interesting aspect there is how do you tokenize experience? So if you're going to use the same kind of transform architecture, which you understand very well and it's really good, how do you actually take a continuous stream of sensory motor stuff and tokenize it in an interesting way? And the same kind of hurdle, I think, is what we see when we try to apply LLMs to analyzing, let's say, biological data, like how do you tokenize that? What's once you've done that step, if you don't do it adaptively, you're sort of beholden to it. And if we can overcome that, it'll be really interesting actually to put these things on actual robots.
So I think Luiz has something to say about
just mention
entanglement.
one thing very quickly. So it seems to me that one approach in AI is to solve the problem by, I have so much compute that it can represent everything possible, and it's all possible in the space, So I use the amount of energy that it would need several planets to harvest enough energy to feed these devices, which it could solve the problem in a sense, right? So you get the whole solar system is a solar panel, and you just feed that into 10 to the 50 parameters or something like that. But that seems to me that's one approach, but it feels that we're missing an opportunity to learn from the system that has, and forget about humans because we've done horrible things. So just take biological intelligence in general.
The bonobos. We're going to imitate the bonobos.
I'm sorry?
The bonobos are cute.
The bonobos are cute. Right. So take bonobos, take birds, take intelligent life forms, and maybe use that as an inspiration to at least an alternative type of approach, because it feels to me that modeling so-called large worlds is not feasible, because you can't formalize all contingencies of every single type of interaction in every single context. It's just combinatorially impossible. So you have to cut the search in some fashion, and if we don't go that route, I think that we're just going to be not destroying the planet, but this next solar systems and whatnot until we get enough energy.
All right. I think, Vincent, you get...
Thank you.
You get the last question of the session. No pressure.
Thank you so much. I'll try to be quick, and thanks a lot for all the stimulating discussion. I'm stuck on one of the things that Taylor said, actually, that really kept burgeoning in my mind. You said people parrot as well, and that's fair, and actually it seems like it's a central feature of semantic memory, if you will. Like, people don't know when they learn things. So, I mean, do you think there's a sense in which what LLMs are doing is some kind of encoding information in semantic memory, and could we, or are you aware of any approach to try to compare how humans perform in the source memory in semantic context versus large language model, or has it been explored at all?
You mean tasks where you have to say where you learned a piece of information,
exactly,
for instance? That's a really good point. No, I don't know of any direct comparisons with language models and people looking at this. I guess there's the topic of hallucination. Like, this is a bad thing in AI systems. They say they read something somewhere and they just made it up. People also do this, of course. Yeah, so I do think there's definitely a commonality there, and that would be interesting to look in a more fine-grained way, like modeling human source memory that way. I do think for lots of important things, people are still much more reliable in these systems and parroting less, though still, disappointingly often parroting things. But yeah, so I think definitely that would be interesting to look at, but I think there are still many areas where the current systems are parroting way too much and more than people would be.
All right. On this note, somebody lost something, so come see me if that's yours. And please join me in thanking all the speakers and panelists. And see you this afternoon. Thanks so much. Glad to conversation.